Welcome back to the next session on operating system. So we're going to start today with virtual memory. Last class we finished our main memory management, wherein we saw how we can get our programs into the main memory, how we can allocate memory to the processes, how we can make the process work together. Multiple processes can be put into the main memory and execute them simultaneously and have a multi-degree degree of multi-programming implemented in our system, right? We saw that we can have the main memory divided into frames and our processes divided into pages. The page size and the frame size must be equal, and we put one page in one frame so that we have less external fragmentation. So today we are going to start with virtual memory. Now what is virtual memory? Virtual memory is an extended main memory. It is a logical address space. It's not a physical address space. Physical address space we call physical address space only to the space or the memory that belongs to the RAM, the main memory, that is the RAM memory. This virtual address or virtual memory is a memory that is there on your secondary storage device, that is your hard disk, because part of the hard disk is used by the RAM as its extended memory. The memory that it will use to save the information or process which are not required to be there in the RAM, and hence it will try to accommodate more processes into the RAM. So we will understand all this with the detailed study of virtual memory, how virtual memory is managed, what things you will put into the virtual memory, and how, if you use it efficiently, gives you best performance, and if you use carelessly, you will get decreased performance. So let's understand virtual memory. We are in unit 4, and this is the second part of unit 4, okay? Second part of unit 4. So let's understand these things about virtual memory. We will first see the background of virtual memory, then we will understand demand paging. Now we have understood paging in our last chapter. In this chapter we are going to understand what is demand paging, and that is what is used by most of our modern computers. And we have page replacement algorithms, we have allocation of frame, and we have thrashing. So these are the concepts that we are going to study in this chapter. So let's understand the background first. See, first of all, I told you that any process that you want to execute should be brought into the main memory. Now think of the program or a process which is to be brought into the main memory. That much memory has to be allocated to that process. So if a process is 200 MB, entire 200 MB of your RAM has to be allocated to this process. Now in a 4 GB of RAM, if you have a 4, nowadays we have commonly 4 GB of RAM in most of the systems. So if you consider 4 GB of RAM, how many processes you can put in of 2 MB, 200 MB. So just think, if you have to load the entire program into the RAM, if the operating system has to be loaded entirely into the RAM, then the amount of space that it will require is in terms of GB, because operating system is in terms of GB, not in terms of MB, right? So now what you need to understand is that the process can be larger than the physical memory. Your RAM is of 4 GB, but your software can be of 5 GB, 8 GB also. So how will you run this process if your process is of 5 or 8 GB and your main memory is of 2 GB or 4 GB? If your main memory is of 4 GB and your process is of 8 GB, then 1 GB is already, one part of the RAM is already consumed by operating system, resident operating system. So the remaining memory is only available to the user process, and you are saying that your process is of 8 GB and your memory is less than 4 GB now, because part of the RAM is occupied by operating system. So what will you do? So what is the best idea is that, I'll give you an example. In functions and all, we cook food in big vessels, but we don't take the entire vessel and serve. What we do, we remove part of it, how much is required, and then serve that food to the people, and then when we finish, then again we come back to take the next lot, right? So this is similar, on the similar lines, this also works. We don't put the entire process into RAM now, because our process is 8 GB and we have less than 4 GB of memory in RAM. So what we do is we only load part of that main code that is required for beginning the execution into the RAM, and we start the execution of the process. Now remember that the process is in pages, and you can fetch any page when it is required and you can start execution. Are you understanding? So this way what we can do is, even if the process is 8 GB and your RAM is less than 4 GB, you can use only 1 GB of space or 500 MB of space for this process, and at a time you can only get 500 MB of data into the main memory. Execute it as and how the other pages are required, it is brought into the main memory. Which pages are not required, put it back. So in this way we are swapping the pages and we are trying to utilize less space and run a big process. So that is what is the use of virtual memory. The space that is required, 8 GB of space that is required by this process, is put into the virtual memory, and into the main memory, the physical memory, we only get those pages that are required currently. Not all is brought into the main memory. So in this way, we can have multiple programs loaded into the main memory and we execute them simultaneously. So when a process is stuck at a particular instruction, we go in to fetch that page. While this process is waiting for that page to be loaded into the main memory, operating system allocates the CPU to another process, and that process is taken for execution. When this page that was requested comes back into the main memory, this process, the first process, is again given the operating system for execution. So this is what is the entire story of virtual memory, how it works. So the virtual memory only works as an extended memory. It only works as a storage system. So to store the extra process information that is required, when it is required, only that time it is loaded into the RAM. So the code needs to be in memory to execute. So we know that the entire code needs to be in memory for execution, as we saw in the last chapter. That was main memory management. Error code, unusual routines, large data structures. What do you mean by this? See, you have exception handling in your object-oriented programming. You don't need to put that exception handling section into the RAM when it is not needed. When the error arises, that time only you need that exceptional handling code. Otherwise, you don't require that exceptional handling. It is once in a way that you will get such exceptions, but you are always prepared for such exceptions. And you have to be prepared for such exceptions, because the user will get panicked if he gets an ununderstandable information of what is happening. So you will write an exceptional code, exception handling code, so that if this situation arises, do this, is what you are telling to the program. But what if that situation doesn't arise only? This code is required? No. So we keep that into the secondary storage. Another is unusual routines. See, there is an routine which is for the US to calculate the corrections, to do the corrections in the balance sheet. This routine is not used since years. So such applications which are written for scenarios that can sometime happen, we keep them into the secondary storage device as an extended RAM, in the extended RAM, and we do not call them until unless it is not required. Even in case of memory, when you allocate memory, for example, arrays, we say we want memory for 100 items, 100 products. But are you always using 100 products? No, you are using only at most 100, in 100 you are using only 10. So you always say array A of 10, 100 by 100. Two-dimension array 100 by 100. 100 by 100 means how much memory you will require? 10,000 space you will require. But are you using always 10,000 space? No. 10 into 10 is 100 what you will be using the maximum. So, the memory that is not required always should not be kept into the main memory and waste that memory. Instead of that, you can only allocate the memory that is required currently, and as and how you require, you go on allocating the memory, so that if there is that memory that is unused, you can give that memory to some other process, and some other process can reside into the main memory, and you can have more degree of multi-programming, and you can have more CPU response, you can have more turnaround, the utilization, CPU utilization and throughput can be higher, and at the same time you will not have increase in response time and turnaround time. So CPU utilization and throughput will be fast if you have this thing. So processes waiting for the CPU will decrease and hence throughput will increase. So we also will require less of I/O. How do you require less of I/O? Now if you have less process in the main memory and more processes residing in your secondary storage extended memory, then you will have to frequently keep swapping between the processes. So since can be reduced because more of the processes are in the main memory, but only the core of them is there in the main memory, and as and how you require the other pages, you are loading that into the main memory. And when this process, when one section is executing, the other section is not needed. One part of the code is executing, the other part of the code is not needed in the main memory. So you can replace that page by replacing the one page by another page. So in this way, you can have, because you are accessing less amount of code from your secondary storage device, the transfer also takes less time. That's what it is. Less I/O needed to swap into the program into main memory. Swapping the entire program and swapping part of that program. Just think, we have calculated the effective time in last chapter. So the time required to swap a large amount of space, large amount of the big process compared to a small page, the time taken for swapping for a smaller page is lesser than swapping a larger process. So that's why we say less of I/O. So virtual memory is what? Virtual memory allocates is a separation of user logical memory from your physical memory. So the secondary storage memory is your virtual memory or your extended memory, and physical memory is your RAM. So the advantage here is only part of the program needs to be there in memory for execution. So only part of that program can be loaded into the main memory and executed, and as and how we require, we load the other pages. Allow address space to be shared by several processes. That is what I explained here. Because we are having only the core program into the main memory, we can have multiple programs. We are not wasting the memory by loading the entire process into the main memory. That is not used, never it is used. That process also, that code also we are loading it to the main memory, and we are wasting the main memory space. Instead of loading that process in that section of the code into the main memory, we'll put that section of code into the secondary storage or in your hard disk and only keep that part of the process that is required in the main memory. So less space is required, so multiple processes can be there in the memory. That's what we say. Several processes can be residing into the main memory. Allows more efficient process creation. So this allows you to create child process creation also becomes very easy with this. Using the fork, you can call the child process, and sharing of memory space with the child process also is very easy with this. So more programs run concurrently and less I/O needed to load or swap processes. So virtual address space. What's the virtual address space? Now we have understood that a logical view of how process is stored in memory. We have seen that. Usually starts at address 0. We consider that it starts at 0, but actually when it is put into the physical memory, it does not start at 0. We consider the logical memory starts at 0. Our process address begins at the point 0, at the address 0. Meanwhile, physical memory organized in page frames. So we have already understood in the last class that our physical memory, that is the main memory, is divided into frames of equal size, right? So the memory management unit must map logical to physical. So last class we have seen that we have our process. So our process starts at logical address space 0, and we have pages of our process, and we have the main memory, that is RAM. This is process. So this is called logical address space. This is called physical address space. And And then we have the secondary storage device, which we call it as virtual memory, right? So the memory that is allocated in your hard disk for doing the task of extended memory is called your virtual memory. So what we do is, now the mapping of which page is in which frame is done using a page table. Last class we have understood. And we have a bit also to indicate whether it's a valid page or an invalid page. So all this we have understood. So memory management unit takes care of mapping your page to your frame. Right? So this is mapping of which page is in which frame. This page is in this frame. This page is in this frame. We get to know from the memory management unit. The memory management unit takes care of managing this page table. So here, virtual memory can be implemented via demand paging and demand segmentation. There are two ways to execute your virtual memory. So this is a diagram that I have just drawn there. This is virtual memory. This is your logical address or your process. This process is larger than your physical memory. If you see, there are more number of pages than the frames available. And first few frames are always used by operating system. So that part you cannot touch. Only the remaining frames, it is your user space. So you need a memory map to say which page is there in which frame. If it is not there in physical frame, then it is in your extended memory. Then you need to have the mapping between the page and the place, your frame in your virtual memory where it is present. So that whenever the CPU generates an address of that particular page, then if that page is not there in the physical memory, it has to be loaded into the physical memory from your virtual memory. Okay? So that is what we are trying to solve here. So in your memory, we have all, if you see the contiguous memory allocation, we have memory divided into core, data, heap and stack. Now we know that the stack grows downward and heap grows upward. What do you mean by this? This means whenever the process tells to allocate memory dynamically, that is malloc, alloc, new, then the heap will allocate, the memory will be allocated from the heap. And as and how memory is allocated, this goes on, the heap limit goes on increasing. So if you have allocated memory by 5 objects, then this much memory is used. Then when you allocate memory for the 6th object, this memory will go up. The limit of this heap will go up. Similarly for stack, if you have variables, local variables declared, that local variables will be allocated space in the stack memory, and as and how you increase the number of declarations, the variable declarations will increase the stack space. So the space between this heap and stack, which is this varying space is called the virtual address space. The virtual pages are loaded into this virtual space, or the virtual, in case of contiguous memory, you don't have pages, you don't divide your process into pages. So in that case, this will be used for shared memory. What is shared memory? Shared library, shared routines, or common tracing code will be loaded into this part of the memory. So that is what is explained here. Usually design logical address space or stack to start at max logical address space and grow down while heap grows up. So stack grows down and heap goes up. So maximize address space used, maximum address space is used, and unused address space between the two holes. This unused address space between the two holes is what is used for your virtual memory. So no physical memory needed until heap or stack grows to a given new page. So enable space address space. So this is called as a space address space with holes left to grow dynamically linked libraries, etc. So you can have dynamically linked libraries loaded in this part. So shared memory by map, share this memory by mapping pages, read write into virtual address space. So this is the virtual address space. You load your shared memory or shared libraries into this page. And it also helps you to create new processes by using the fork, because if this process wants to create a child process by sharing this part of the code with the child process, then you use the fork and you specify this address for the child process to be used as shared memory. Okay, so that is what is shown in this next diagram. So two processes are there, and one process is a child of another process, or it is an independent process created by this process. It says that you can use this shared library, these shared pages that are of one process can be used by another process. It is only that the shared library will have the address of this shared pages, and they both will be accessing the shared pages. So that is what is the use of having virtual memory. So you can have the shared library stored into your secondary or extended virtual memory and used called only when it is required. So the best way of solving virtual memory to manage your pages is to have demand paging. So what is demand paging? I explained you at the beginning of the class that when you require to start an execution of a process, you only load. For example, if I tell you with code, with a program, supposing I write a C program like this, main, so in this program, consider that main is one page, add is another page, this is page 1, and subtract is another page, this is page 2. Okay, so now when your program execution starts, do you need these two pages to be in the memory? No. We start their execution with main, right? So only the main code has to be there in your physical memory. So you start executing, okay? Supposing you have your clear screen function, you have a printf function, right? We need that also, no? So I have not written that. So what will happen? CLR is what? It's a built-in function. So built-in function, that is one page. So main page is loaded. Now when SLR is needed, only that time that page is loaded, so that the display is cleared. Whatever was there before which is removed, that particular information is, the screen is cleared. So for that you will call this method. So this is page dynamically loaded, right? So this is a this is a library, shared library. You can use this library by multiple programs simultaneously. Multiple C programs can use clear screen function simultaneously. So we can load this only when it is required. If it is not required, don't load it. So you first call this page. Okay, so page 0 is loaded into RAM now. Apart from that, clear screen page is also loaded. You clear the screen. After the task of clear screen is done, will you keep that into the main memory? That is no need in further statements, right? So we can remove that page from the main memory. The next page that is required is add page 1. So we load that page. Then after addition is done and we print the value of addition. For printing you need the printf function. So we load the printf function by removing the add function. Then after printing that, we need the subtract function. So you can remove the printf function and load the subtract function. After loading the subtract function and calculating the subtraction, then you will need the printf. Again you will load the printf. So what is happening here? We are not loading the entire program at the same time in the RAM. What we are doing is, in the RAM, we are only having the main. Okay, the main page is always there because it is the heart of the code and it has to be there. So here CLR SCR is loaded. So CLR SCR will finish cleaning the screen. Then this will be removed because its task is over. Then add function is loaded. In the same place, add function is loaded. Add will be calculated, is executed, and it will calculate A plus B and return C to main. Okay. Then after C is returned, printf is required. So we will load printf. So what is it? When required, that time we are calling that page. So that is why it is called demand paging. On demand, you call a page. When that particular instruction requires a page to be loaded, that page is loaded. So this instruction we are executing, and for this instruction the page required is add page. So load add page. For this instruction subtract is needed. So load subtract. When you are executing printf, printf function is needed. So load printf. I am telling you in terms of modules, which is subroutine in demand, so segmentation, demand segmentation. But same way you can have pages. So you can have all the entire program divided into equal page, and that particular page what is required, this instruction is in which offset of that page will be loaded into the main memory. So this way we will have demand paging executed. When that page required, that time only you open that page. Like we give you an assignment and you open the book and the page only that time when the assignment is given. Otherwise you don't do it on yourself. You don't open and see even the videos. You are not opening and seeing the videos on your own. When we give you an assignment to solve, yesterday I gave you banker's problem to solve, that time you are asking me which video we should refer, right? So that is when demand is there, that time only you go and watch the video. So when demand is there, that time only the page is loaded. So that is what is demand paging. So could bring entire process into memory at load time. So if you bring the entire process into memory at load time, what happens? A lot of memory is used and it's a waste of memory. So what you do? Bring a page into memory only when it is needed. Best solution is bring the page when it is needed. If it is not needed, don't bring that page. Sometimes we don't call a function in our project. We write a lot of programs, a lot of classes, a lot of methods in the classes, but we don't call all of them always. Only when it is required, we call them. Like for example, once a person finishes login, do you require login till the end of his session? No, you will not require login till the end of his session. You will be doing various tasks in that particular project, various programs for code you will be executing. But you will only go to log out, you will not go back to login until unless your session doesn't end. So that is what is demand paging. When required, that time only you call that page, otherwise not called. Okay. So less IO needed or unnecessary IO is happening, less memory needed, faster response, more users can use your RAM. That is what is the advantage of having demand paging. So similar to paging system with swapping. So the diagram here shows you that it is same like your paging system, wherein your process is divided into pages and your main memory is divided into frames, and we do swapping. Here the swapping is not a normal swapper, we call it as a lazy swapper. Why is it called a lazy swapper? Because we are not swapping the entire process in and entire process out. We are only swapping the page that is required. So it is called as a lazy swapper. So we were here. So we said page is needed, reference to it. So invalid reference, abort, not in memory, bring to memory. So two things happen. We have an valid and invalid bit set again here, like we had in the previous main memory management. Here also in the page table, we have page number, which frame it is in, and whether it is valid or invalid. So if it is present in the physical memory, then the page is valid and it is indicates to the operating system that this particular reference is for the process, the page that is there in main memory, it can be directly accessed. But if the page is not there in main memory, it is there on a extended memory or your virtual memory, then the bit will be set to invalid. And then the operating system has to take care of loading that page from your secondary memory to main memory, and then the execution of that process continues from the point where it has stopped. So we'll understand that, how that happens. So you just understand now that if it is an invalid bit, then we abort. If it is not in memory, we bring back in the main memory. So lazy swapper never swap a page into memory unless page is be needed. Swapper that deals with page is called a pager. So this is not a normal swapper, it is a pager. Why it is a pager? Because it will get swap page in and it swaps out page. The page swapping is happening, so that is why we call it as a pager, and it is called a lazy swapper. Okay. So basic concept here with paging, pager with swapping, pager guesses which page will be used before swapping out again. So this is the algorithms that we have of allocating frames and to pages. We'll see this in the next section. So instead of pager brings in only those page into memory. So instead of removing the required page, so I did not remove the main page. You all saw that? Because main page is what is going to be used continuously. So we are not replacing the main page. What did I do? Instead I took another frame wherein I loaded these pages that are required at that time and again removed it when that are not required. So that is what is this pager doing. So it will remove the page only that is not needed. If it is needed, it will be placed there only. So main program is not removed. The other frame is used for swapping of the pages. So I put the page when it was required, I removed the page and got another page at the same place. So that is what is this task of demand page. Required. So if page needed and not memory resident means it is not there in the main memory, it's not in the physical memory. Need to detect and load the page into memory from storage. So it will be there in the storage, get it into the memory without changing program behavior, without programmer needing to change the code. So programmer doesn't have to bother about anything now. So we have a valid or an invalid bit to tell whether that page is there in the main memory or no. So whenever there is a V, it indicates that this bit is valid, this page is valid, and these are invalid. A page is valid means this has this page number, we know which frame to access. So it is valid. For this page number, the bit is invalid means there is no frame allocated to this page. So you have to go to secondary storage and see whether this page is present. If it is present on the secondary storage means it is a valid request. If it is a valid request, bring that page from the secondary storage to the main memory so that the program continues execution. So during MMU address translation, if valid invalid bit in page table entry is I, then it generates a page fault. The page fault is an interrupt signal to the operating system. It's a trap for the operating system. So operating system has to jump in and resolve this issue. So this is the diagram. Here we have the logical memory. The logical memory is nothing but your process. This process is divided into 7 pages, and these are the 7-page frame mapping, the page table. So in this, only 3 pages are there in the main memory. Other pages are stored in your secondary memory. So what happens now? When CPU generates an address and it says, I want to access page 6. Page 6 is there in this. What is page 6 bit? It is invalid. Invalid means that this page is either invalid or it is not there in physical frame. You have to bring it if it is present in the secondary device. So go to secondary device. Page 6 is G. This is a page 6. This page is in secondary device. So it means that it is a valid page, valid request generated by the CPU. So what it has to do, operating system will see a free frame from this frame and load this into that frame and reset this particular value to the frame. So if it is loaded in frame 10, 6, 10 and this will be made valid. So whenever the page is there in the RAM, which means that the page is valid, so you will have a valid bit. If it is not there in the physical frame, if it is in the secondary storage device, the bit will be indicated as invalid. So what is a page fault? A page fault is an interrupt that is generated when a page is requested, a page reference is requested and the page is not present in the physical memory. So if there is a reference to a page, the definition is if there is a reference to a page, the first reference to that page will track to the operating system page fault. So if the page is not present in the main memory, it will generate a page fault. The first reference to it will always generate a page fault because all pages are loaded in your secondary storage device and as and how the page is required is loaded into the RAM. So first reference will always cause a page fault. Operating system looks at another table to decide whether it is valid or invalid. If it is a valid reference, abort. If it is an invalid reference, abort. If it is a valid reference, just not in memory. It means that the page is not there in physical memory, it is there in secondary memory. Find free frame. So first task that it will do is, it will find a free frame. If the free frame is available, then it will allocate that frame to that page, or else it will see which page is not needed and it will remove that page from the main memory and make a frame free. Okay. So swap page into frame via scheduled disk operation. So for this swapping of page, getting the page from the secondary storage device to the main memory, it will generate an IO read statement. So a reading of the IO disk is nothing but IO of the input-output operation of your disk management. So it performs an IO to the disk. So it is an reading operation of the disk. The reading operation will cause an IO instruction to generate. So read the instruction and load that particular memory data into your physical RAM. So that is loaded and then reset tables to indicate page now in memory and sets validation bit to V. So validation bit V indicates that the frame, that page is present in a physical frame. Restart the instruction that caused the page fault. Let's understand the same thing with a diagram. Now, I'll explain the same code with the help of this diagram. So apart from add and subtract, we have a page for CLR, SCR, and we have one more page for printf. Okay, so this is page 1, page 2, page 3, page 4. So 4 pages process we will consider. So we are dividing the page in terms of functions to understand it better, but these are process pages. Just understand that they are process pages. Don't worry, don't say that they are not of equal length and all that. This is just an example that the process is divided into pages. Okay, fine? Okay. So first, the first instruction is clear screen. So this is what? This is declaration of variables. Declaration of variables are not part of your execution. For that, the memory is allocated by your loader and the memory is specified where it has to be saved. This A and B values. Okay. So supposing if A is equals to 10 and B is equals to 5. Okay. So there is memory allocated for them in some part of one page. Some page there is memory allocated to them. So you just understand that much right now. Okay. So first instruction, that is see. This is the first step. Reference to a page. So which page I require now? This is CLR-SCR. CLR-SCR is page 3. I require page 3. So in RAM, main memory is here, CLR-SCR. Then after that CLR-SCR, you have P is equals to add A comma B. The next statement you will have is printf P. The next statement you will have is C is equals to sub A minus B. And then you have printf statement. So this is your main program. So one frame is allocated to that. So the first instruction in this page execution causes a page fault. It requires CLR-SCR. CLR-SCR is not loaded in your RAM. So it sees whether, let's do the page table also. So let's have a page table also. So this is a page table. You have page 0, then you have 1, 2, 3 and 4. So we have 4 pages. So page 0, this is page 0, right? Page 0, supposing if it is loaded in frame 4. So frame 4 and valid. Okay. Now CLR-SCR is page 3. So reference is for page 3. Page 3 is invalid. Why? Because it is not there in physical memory. Since it is invalid, 3 is invalid. So the invalid, can you see here? I is there. Invalid means it generates the second step. It goes and executes the second step. Second step is a trap to the operating system. It executes, it initializes a interrupt to the operating system. The interrupt to the operating system sends a signal that it needs page 3 and the bit is invalid. So these two information it sends to the operating system. The instruction is, I need page 3 of this process and its bit is set to invalid. So operating system checks whether this page is a valid page from this process only or no. So it says, yes, this is from the same process. So it is a valid page. If it is a valid page, page is in backing store, is step 3. Can you see there 3 on top? It goes to the backing store. The page is present at this location. So the fourth step that it does is bring a page, missing page in the main memory. So page 3 is loaded in frame 5, CLR-SCR. So the page is loaded into frame 5. So 3 will be allocated frame 5 and bit will be turned to V. So that is what is the fifth step. Reset page table. We just now did the page table reset. So reset page table. So that page table is reset. Here you will get the frame number and this bit will be made V to indicate that it is a valid page. Once that is done, the information is sent to the process that CPU will start executing from that instruction where it had stopped. Where it had stopped, the process was interrupted at CLR-SCR. So the CPU will jump to frame 5 and start executing this CLR-SCR. Start working in clearing your screen. After the screen is cleared, then it goes to the next instruction. C is equal to add A comma B. Now there is another page request. This page is page 1. So again it goes to the page table, checks that the bit is invalid, page is not allocated a frame. So it again generates a trap. So again step 2 is executed. Operating system checks that is this a valid reference or no. Yes, it is a valid reference because this process is having page 1 as a valid page. So it will do what? This page is not needed any further. So it will remove that page and at frame 5 is become free now. So it will load page 1 which is there on the secondary storage device. It will add the method add to your frame 5. So this bit will be invalid now because it is removed and 1 will be set 5 and it will be made valid. Did you all get that? So that is how this process works. So first step is it makes a reference for the page, checks the page table. If that page is not present in the page table, it goes to the operating system, complains to the operating system, this page is not present in the frame in your physical memory. So So it checks whether it is a valid reference or an invalid reference. If it is a valid reference, it goes to the backing store, gets that page from the backing store into the main memory, resets the page table, and tells the operating system, tells the CPU to continue the execution of this process from where you have stopped. Clear? So this is demand paging. So what we have here, extreme cases. How we can do this? Now initially I started with first frame, main frame in the main page, loaded into the thing. So what happens if you don't have this also? None of the pages are loaded. All bits are invalid. All page bits are invalid. In such a case, its operating system has to see which page is the beginning page and load that page. So the first page itself causes a page fault. A process with no page loaded into the main memory, from the first page itself, from where it should start execution, from that page only, if there is a page fault generated to the operating system, then that kind of a scenario is called pure demand paging. That is one case. Another case is, actually a given instruction could access multiple pages. Supposing you will have another program where you are saying P is equals to Fibonacci of 3 into Fibonacci of 4 divided by Fibonacci of 2. You can have this as, this is nothing but 5C3. What is 5C3? Permutation combination? Combination of 5C3 is this calculation. So how many functions you all are calculating? Here it is the same function. So let me take out some other examples. Square root of 26 divided by pi. I am writing a slash like this, it has to be like that, but just understanding that we are calling now two functions. Two functions is two pages. So one instruction is making reference to two pages. So that also can be done. You can have multiple pages called simultaneously. So in that case, we call this as locality of reference. And this decreases the pain of swapping, because same time you are swapping more than one pages. So you are swapping a set of pages simultaneously. So you are making a read IO instruction to the disk with multiple page or multiple memory locations to be loaded simultaneously. So it is called as locality of reference. So you are doing multiple pages loading simultaneously, multiple frames. Even in your virtual memory is also divided into frames of the same size. So multiple frames of your virtual memory are loaded into your physical memory page frames. So that is why it's called locality of reference. So hardware support needed for demand paging are page table with valid invalid bit, that is required. Then secondary memory, swap device with swap space. So you need a device which will allow you to do swapping of instructions, and instruction execution restarting. So it will stop somewhere. So you have to start from the same instruction execution. So that is the hardware that is required. Then next is what is the performance of this demand paging. This entire process is explained in this step. Just go through the steps, then I'll explain you all what it is. This is called stages of demand paging. You relate this to the diagram that we saw, then you all will be able to understand each of these steps. So first is swap to the operating system. Step 2. Second, next, save the user register and process state. So this was not told, but when a trap to the operating system is sent, the operating system, first thing that it will do is, it will remove whatever is the CPU's current status, put it into PCB and save that process into the waiting list. Put that process into waiting list because it has asked for something and I have to fetch that something and get it, right? So it will take some time. By that time, the CPU can execute some other process instead of sitting and waiting there for doing nothing. It can go and execute another process. So the CPU first will take the state of the process executing and put it into PCB and put the PCB into waiting list, waiting queue. Remember, you all have learned this in chapter number 3, what is PCB and what is waiting queue. So just check in the internals, you all have written all this, right? So that is what we are doing. So we take the snapshot of the process, current state of the process, put it into the PCB and store this PCB into the waiting queue. Next, determine the interrupt was for a page fault. Check what kind of interrupt that process has generated. Is it a page fault interrupt? Process can interrupt for multiple things. It can interrupt for IO request. It can interrupt for other services. It can interrupt saying that something else is wrong or something. Whatever it is, operating system has to check what interrupt signal it is, what is its question, what data it has sent. It will verify all that and then do the task that has to be done. To do that task also, it has to load a routine of itself, operating system routine, interrupt signal, vector. It has to check the vector. What is this interrupt? What action has to be taken for that interrupt? It loads that code that takes care of executing this process. Whatever process has to be done for that, there is a process and that process is having a code and that code is loaded into the transient operating system. So it determines what kind of interrupt is it. Is it a page fault? Yes, it's a page fault. Check that the page reference was legal. So first thing that it will do is will check whether the page reference is legal. If the page reference is illegal, determine the location of the page on the secondary storage device. Where on the secondary storage device this page is available. Pick from there. Then issue a read from the disk. So it will generate and it cannot directly fetch the data because the data is in with hand of whom? The hard disk. The hard disk has to give the data. To get that data from the hard disk, it has to make the disk to go and fetch that particular memory location. So it will tell the disk, go and fetch this particular disk. On that disk, there is this sector. In that sector, this page is there. Get that page into the main memory. So allow me to read that data. So that is what is it doing. So it frees a frame and waits in a queue for the device until the read request is served. So process is waiting in a queue until that page is read from the secondary storage device into the main memory. Wait for the device seek and or latency time. So that disk also will have its own pleasure. It will read that particular sector and it will give you that particular data. So after it does that, begin the transfers of the page to a main frame. So after it seeks that particular section, we will see this in the next chapter, how disk reading does. What are the different algorithms for disk reading. There are different algorithms for disk reading as well. So it goes and reads that disk, and when it reads that disk, the disk is stored this particular memory, this particular address of your frame, of your of your RAM, sorry, of the main memory. This particular page from the secondary storage device has to be loaded. So the transfer of page to the free frame is done. Once that is done, while waiting, allocate the CPU to some other user. So this process is gone into P1 is gone into waiting. So P2 process is allocated to the CPU for execution. Meantime, so receive an interrupt from the disk IO. Again, the operating system gets an interrupt signal from the hard disk saying that yes, whatever you had asked for, I have put it into the RAM. You can take it and you can utilize it. So that task, that interrupt signal also has to reach to the operating system. So receives an interrupt from the disk subsystem. IO completed. IO reading is completed. If IO reading is completed, then that process P2, P1, which was put into waiting state, which had generated a page fault, is brought back into the main memory for execution. So it's removed from the waiting list and put into the frame for execution. So determine that the interrupt was from the disk, check whether it is valid, correct the page table and other tables to show page in the memory. So do the page table, you have to update the page table that this frame is allocated to this page number. So correct the page table, wait for the CPU to be allocated to this process again, and then restore the user registers, process state and new page table, and then resume the interrupt instruction. So this is the entire process that takes place. In the diagram we have showed you only 6 steps, but actually there are so many 12 steps that are taken to take care that the process when it generates a page fault, it gets back the page into the main memory and continues its execution. Next is performance of a demand paging. So if you see, if you consider that the page fault occurs p number of times for a process, this can be 0 or 1. 0 indicates that never a page fault has occurred, and 1 indicates that every page the page fault has happened. So it's a pure demand paging. P is equal to 1 indicates the pure demand paging. Means from the first instruction only the operating system has to load the main code into the main program into the RAM. So from there only the page fault has occurred. So that's why it is called as a pure demand paging. So every page reference is a fault. So if P is 1, every reference is a page fault. Every reference indicates a page fault. So what is the access time here? ETA? ETA is 1 minus P. What is 1 minus P? Total number of page faults can be 1. But number of page faults occurred is P. So 1 minus P into memory access time. So that many times you access the memory plus P into page fault overhead. So if number of page faults didn't occur in that much times you access the memory directly. If page fault has occurred, then page fault occur overhead. Operating system has to come into picture, get that page from the secondary storage device, make the disk to read the page, get that page into the main memory, swap that page out, swap that page in. So all this process, the time taken for all that